And we're live. Thank you so much for tuning in today. Today, we're going to cover a topic which I find very interesting, which is scaling laws. We're going to talk about both how AI scales and how compute in general scales. And I've always thought this was an interesting subject, but in my last stream, I reacted to a video where Dwarkesh interviewed Satya Nadella, and the CEO of Microsoft, and he said something really interesting in that episode. He said that intelligence is the log of compute, and this was one of his theses. And as he thought about building a hyperscale AI infrastructure company, this was one of the things that he thought was true. And so I thought this was very interesting, and I looked deeper into why he claimed that this was true, and I found this to be fascinating. So let me set the stage for what exactly this means. So actually, let me pull up an image of a log graph. Log graph. I'm just going to Google this. Okay, so here's a log graph. If you see this, I'll try to make this bigger even. I'm going to pull this up. What's the best one to show? I guess this is okay, but like look at this part of the graph here. What happens is as you add more of something on the x-axis, it goes up by less and less on the y-axis. So imagine that this is the intelligence is here on the y-axis. And so you want something to look like this. You want something to go up. If you want a very intelligent AI, you want the curve to go up very steeply because that means it will be getting way more intelligent. So the higher, the better. Let's think about it that way. And that now let's imagine that on the x-axis is the amount of computing power that you have to train and run your AI. Now, when Sam Altman and Satya Nadella say that intelligence is the log of compute, they mean this axis, this y-axis here is intelligence, and this x-axis is compute. And I'll describe this for those who are listening on audio, but essentially what happens is, as you can see, there's kind of like a plateau here. As you increase a lot more compute, it only gets slightly more intelligent. Let me see if there's any better visualization here. Yeah, see, this is more what I was thinking. This is a simpler example. You see here that starting at 0, now you're increasing the scale. You're going far along the x-axis, and you're only going a little bit up. You can see that this is basically flattening out and approaching some sort of maximum value. And essentially, that is what log scaling is. So I thought it was really interesting when Satya Nadella, on one hand, he said he wants to build, his thesis is that there's going to be, it's going to be great to have the biggest data centers and be one of the biggest providers of AI infrastructure. And this is going to be a really good business model. But on the other hand, he basically also admitted that this is maybe not the best moat, because if you have a ton of servers and a ton of GPUs and a ton of compute resources and you put it to use for AI, it's interesting because as you can see, there's a diminishing return on this compute. And I did not get an adequate answer for why that doesn't give him pause about his model, but I don't have the answer. I won't present you the answer now, but what I want to do is I want to go and look at the other implications of this. So first of all, though, what I want to say is I think that if this is true, this is bad for companies like Microsoft that want to build a lot of infrastructure. And it's interesting that even though it is bad for them, they still believe it's true. And so let's look into the evidence of this. Let's look into the evidence of this, and then we'll get more into the implications. So, as I think, when was this posted? This was posted pretty recently. But Sam Altman recently, in February 9th, 2025, posted this article called Three Observations. And one of these observations that he made was this one. This is the first and foremost observation that he made. He said, intelligence of an AI model roughly equals the log of the resources used to train and run it. These resources are chiefly training, compute data, and inference compute. It appears that you can spend arbitrary amounts of money and get continuous and predictable gains. The scaling laws that predict this are accurate over many orders of magnitude. So this is super interesting. So here's the thing that gets AI people excited about this, people who want to see AI scale, like OpenAI and Microsoft. They get excited because they don't ever see improvements. The improvements never stop coming. If you have more data, more compute, and more ability to train and run inference, the more of that you have, the better the results will be. So that's super exciting. There's not going to be a point at which we just don't know how to make it better, where we just hit a wall. At least so far, we haven't encountered that. But the trend is not looking too good, because the implication of this is that if they just keep building bigger data centers, it's going to cost more and more and more to do that. Like 10 times more to build you have to build a 10 times bigger data center. It's like way more expensive than the previous one. All of that is still true, but you're only going to get a slight improvement in the intelligence. And so as the leaders in the space, they may have a lot of infrastructure and capital, but that capital is actually not a really strong moat for their businesses. Let's plot this out. Actually, let's go to Wolfram Alpha and see if we can plot this. I just want to kind of drill down on this a little bit just to kind of paint this picture. Let's just say log X. Let's see what happens if we paint this. I wonder, is there a way to, I don't even know. I don't have a pro account on this or anything like that. Well, so, okay, let's just do an example here. Let's say log of 10. Okay, log of 10 is, or it doesn't matter, log, ln, log of 2. Let's just say log of 10 is 2.3. Okay, now what's log of 100? 4.6. Okay, so I want to make this really clear. So log of 10 was 2.3. I'm just typing this here because it's easy to show you. Log of 100 was 4.6 or something like that. So what happened? Imagine that you had a $10 million data center. And if you had a $10 million data center and you got an intelligence score of 2.3, let's just say. And so if you doubled that and got a $20 million data center, you'd think you spent twice the amount of capital. So you should get twice the result. That would be linear. But that's not what it is. Really what it is you have to spend 10 times the amount of resources to get double the result. So if you start at 2.3 and you double that and get to 4.6 amount of intelligence points, however you want to quantify that, and IQ is a very tricky measure, but so we'll just kind of be abstract about this. And then if you want to do that again, you're going to have to do log 1,000. Let's say you have, so a 1,000 million, $1 billion data center to get even less than 10 intelligence points in this scenario. So you can see how maybe in the beginning, it makes a lot of sense. You can just keep scaling this, but at some point you're not going to be able to continue scaling because the returns are going to be just so low. And and also kind of, you have to remember how exponentials work. So if, for example, if you thought it was a big deal going from 10 to 100, then you have to realize you did 10 times to get to 100. If you thought that was a big deal, going from 100 to 1,000 is way bigger because now you're doing 10 100 times. So if doing 10 in the first place was a very large investment for you, then and going to 100 was like really pushing your limits, it's not like you can just incrementally, up that to 1,000, to like an investment level of 1,000. Maybe this is kind of abstract. I'm just trying to paint the picture for why at some point we're going to hit a wall and we're not going to be able to continue increasing the amount of compute. And we're going to basically be at our economic capacity. And this economic capacity we're going to be fully saturated. We're going to have as many GPUs as we want. And yes, we can increase the amount of GPUs by maybe 8% or something along those lines, or 4%. We can maybe match economic growth in the amount of GPUs that we create and the amount of compute resources that we provide. But at some point, we're not going to be able to just keep 10xing it. That's not going to work. And one thing I tried to do in preparation for this stream was I was trying to like actually dive into some papers and actually show you the results that substantiate this claim. And I think I'm going to keep researching this because I think that there is it's a little bit tricky because there's a lot of different ways that people come at this. Some people talk about that there's a power law in the loss in training, and then some people measure intelligence, and they do actually show like this log scale performance. So there's a variety of different ways. I'm still kind of parsing through the literature, but I think this was a really good article that kind of talks about it, and I'm going to show you a video too. So what Toby is saying here is that as you increase, so this is O1's results. And on the left here, I'm going to try to make this bigger. On the left here, it is the x-axis has train time compute, and then there's accuracy on the y-axis. And so the other one is the same thing except it's test time compute. And so basically the point is both of these graphs have compute on the x-axis and accuracy on the y-axis. So accuracy is very similar to intelligence. You can think of it that way. It's like the performance, the results, how good is this model? And on the x-axis is how much computational power is put into it. And so if you look at this, and if you're listening, I'll just describe it to you, but if you see these graphs, the dots are basically in a straight line. So that appears to be good. It means, and this is what you would expect. You would expect if you put more compute, you would have more accuracy. Bigger computers, more GPUs, better results. That's very straightforward. But the nuance here is that these x-axes are log scale, meaning that actually every time you think that you go one notch over, you're actually going 10 times over. So it's like 10 instead of 1, 2, 3, 4, 5, 6, like that on the x-axis. It's 10, 100, 1,000, 1 million, or no, not 1 million, 10,000. You get it. 10,000, 100,000, 1 million. That's what it really is. And so actually, this doesn't look like a straight line, and this looks like something that is plateauing. This, if you were to graph this normally, this would look like something that's getting diminishing returns. And as you add more compute, you're not getting as much out each time. Every time you double the compute, you get less and less out. Let's continue looking at this. So he gives this example of Moore's law, and this is something we'll talk about a bit more, no pun intended, later. But this is the inverse of what we're looking at, essentially. This on the x-axis here is linear. It's 1970, 1972, 1974, blah, 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 all the way to 2020. And this is a log scale y-axis. And this looks like a straight line. And so, but as we all know, compute increases exponentially. It doubles every 18 months. So now realize that given that these axes are reversed, then you have to understand them. What that means is the way you should think about this is like as good as computers are at increasing, that's how bad AI is at scaling proportional to the amount of resources provided to it. So just by increasing compute and increasing resources, you're not actually it's actually quite a bad scaling characteristic. And so let's see if there's anything more worth pulling from here. Oh yeah, this was good. This was good. So this is O3. And as you can see here, this is very clear. $1. So we're looking on the x-axis. We're saying how much did we spend to get the result? So $1 is the first notch on the x-axis, then $10, then $100, then $1,000. That's O3 high tuned, $1,000 to get a result. Well, you see the results are very good. Again, we can just kind of like draw a line here and show it go right, pretty straight up. Like you spend more, you get more out of it. But like, for example, on this one test, O3 high is getting 88%. Whereas like much of the older models, like, for example, O1 high, which is I think O1 Pro, that's only getting like 32%. So it's way better. But O1 is spending less than $10, I think, or at least like around $10 per request. That actually sounds kind of crazy. Is that true? Well, whatever. I don't know about that, but it's spending less, let's just say less than $10. I think it must be less than $10. But O1 is spending over $1,000. And in fact, it might be more like $5,000 on this graph, or $6,000 per request, because it seems to be pretty far out there, like closer to the 10,000 than the 1,000. So the point is that this is also following this trend. This is more evidence of this following this trend. Let's see if he put some lines over this graph. Okay, that's not super helpful to me. No, he did do some analysis here, but I didn't really get into this. So let's not talk about this part. But I think the point of this article is to talk about, like, this was already basically, he's kind of already taking for granted the idea that we have this log scale performance characteristic in training. So when you train, like train time compute, you add more train time compute when you're training, building up your model. When you're doing all of that, you get this result. But it also follows from test time compute. So meaning when you actually add more inference compute and you run the model for longer, and you basically scale up the amount of like the chain of thought, and you like after you've built the model, when you run, basically, to simplify this, let's say you build up the model, it's already built, and then you run it on a more powerful hardware. Having that more powerful hardware also has the same diminishing return. So we're seeing this trend again and again. And this is very interesting. I mean, this is pretty bearish, actually, for the big labs whose strategy is to just have the most compute. They're going to spend a lot more money, and they're not going to get a lot more out of it. I think what we should do, I want to watch some of this video here. This is a really good video that talks about some of this stuff. Let's do a little quick react to this video, and then I want to talk more about the implications of this. So yeah, let's get started.
AI models can't cross this boundary, and we don't know why. As we train an AI model, its error rate generally drops off quickly and then levels off. If we train a larger model, it will achieve a lower error rate, but requires more compute. Scaling to larger and larger models, we end up with a family of curves like this. Switching our axes to logarithmic scales, a clear trend emerges, where no model can cross this line, known as the compute optimal or compute efficient frontier. This trend is one of 3 neural scaling laws that have been broadly observed. Error rate scales in a very similar way with compute, model size, and dataset size, and remarkably doesn't depend much on model architecture or other algorithmic details, as long as reasonably good choices are made. The interesting question from here is, have we discovered some fundamental law of nature, like an ideal gas law for building intelligent systems? Or is this trend just a result of the specific neural network-driven approach to AI that we're taking right now? How powerful can these models become if we continue increasing the amount of data, model size, and compute? Can we drive errors to zero, or will performance level off? Why are data, model size, and compute the fundamental limits of the systems we're building? And why are they connected to model performance in such a simple way? 2020 was a watershed year for OpenAI. In January, the team released this paper, where they showed very clear performance trends across a broad range of scales for language models. The team fit a power law equation to each set of results, giving a precise estimate for how performance scales with compute, dataset size, and model size. On logarithmic plots, these power law equations show up as straight lines, and the slope of each line is equal to the exponent of the fit equation. Larger exponents make for steeper lines and more rapid performance improvements. The team observed no signs of deviation from these trends on the upper end, foreshadowing OpenAI's strategy for the year. The largest model the team tested at the time had 1.5 billion learnable parameters, and required around 10 petaflop days of compute to train. A petaflop day is the number of computations a system capable of 1 quadrillion floating point operations a second can perform in a day. The top-of-the-line GPUs at the time, the NVIDIA V100, is capable of around 30 teraflops. So a system with 33 of these $10,000 GPUs would deliver around a petaflop of compute. That summer, the team's empirically predicted gains would be realized with the release of GPT-3. The OpenAI team had placed a massive bet on scale, partnering with Microsoft on a huge supercomputer, equipped with not 33, but 10,000 V100 GPUs, and training the absolutely massive 175 billion parameter GPT-3 model, using 3,640 petaflop days of compute. GPT-3 performance followed the trend line predicted in January remarkably well, but also didn't flatten out, indicating that even larger models would further improve performance. If the massive GPT-3 hadn't reached the limits of neural scaling, where were they? Is it possible to drive error rates to zero given sufficient compute, data, and model size? In an October publication, the OpenAI team took a deeper look at scaling. The team found the same clear scaling laws across a range of problems, including image and video modeling. They also found that on a number of these other problems, the scaling trends did eventually flatten out before reaching zero error. This makes sense if we consider exactly what these error rates are measuring. Large language models like GPT-3 are autoregressive. They are trained to predict the next word or word fragment in sequences of text, as a function of the words that come before. These predictions generally take the form of vectors of probabilities. So for a given sequence of input words,
Right now, basically, we don't need to necessarily get into how LLMs work, and we're not going to go through this whole video, but you can see how there are these scaling laws. Like if we go back here, like these are log graphs, and we see this straight line. So this is not a non-log scale, and this is a log scale. On the x-axis, we see this straight decline in the loss. And so loss is bad. So you want loss to be low. So that's the same thing basically as going the other direction, where you are having more intelligence. Basically, it's one way you could think about it is if it was going up and intelligence was here, down and loss. It's roughly the same type of a thing. So he's going to explain how LLMs work. And I watched this, but now I'm trying to remember if there was something else worth covering here. Maybe let's just watch a little bit more. Let's just skip ahead past this LLM description. I do recommend this video. And just so you know, I have on my channel, I have this playlist where I save videos that I've reacted to. So it's called Sources. You can go on my channel, and if you like this kind of thing, subscribe. I have a lot of great reactions to really insightful videos. I cover a lot of AI topics, tech, all that kind of stuff. So please subscribe if you like this. But you can go and watch this video. It's in my Sources playlist. But let's skip ahead and then let's continue watching.
Model at index 42,590. So if our model is 100% confident, then our cross-entropy loss equals the minus natural logarithm of 1, or 0, which makes sense and matches our L1 loss. If our model is 90% confident of the correct answer, our cross-entropy loss equals the negative natural log of 0.9, or about 0.1, again close to our L1 loss. Plotting our cross-entropy loss is a function of the model's output probability.
Right. Okay. So actually, we don't need to cover this. This is more of like a detail of the math. Let's not get into this, but this described quite well the empirical data that supports this claim, that basically there is a diminishing return for adding compute to scale. Now, there's one. So now, before we get into like the analysis of this, there's kind of one other thing I wanted to think about. So there's this idea of Moore's law, and we've talked about Moore's law, and that's that compute doubles every 18 months. And the compute capacity essentially. And it was first about like the number of transistors. And now we kind of have like a more abstract conception of Moore's law, which is basically just computational power. And there's a slightly different Moore's law for like GPU flops. And there's one that's like if you take, it's slightly different if you take into account like parallel computing and all these different things. So I don't want to get caught too much on the specifics of that, but there's this other thing called Nielsen's law, and I wanted to talk about this. So Nielsen, I believe they're like a company that measured who people watched on TV, like that's their original thing. They had all these metrics on what TV shows people were watching and stuff like this. But they also, were in the telecommunication. They're basically a major player in the telecommunications industry. And so one of the things that they have noticed is this thing called Nielsen's law, which is about internet bandwidth. And so internet bandwidth, so we're talking about home internet connections, high-end home internet connections. And what we've noticed, what Nielsen's law has noticed, is that these also are scaling exponentially. And so you remember the dial-up days where a lot of people won't remember this, but like there were times where you couldn't use the internet because you were on the phone, and then the internet was so super slow and you hear these like tones, and like there's a time where it was just a much less capable network. When you were at home, you were not able to download as much as you can now. Now, from a home internet connection in a major city with good infrastructure, like the average person is able to download insane amounts of data super fast. Like we're talking about like gigabits, or even 2 gigabits at this point, or 5 gigabits. I mean, I've seen 5 for home. I think I might have seen a 10 gigabit connection for home. I'm not sure about that, but I've definitely seen 5 gigabits at home. It's not available in my area, but some neighborhoods in my city do have that. And so so internet has increased a lot over the years. And the thing that's interesting though is that it has not been as good as Moore's law. Moore's law has scaled more than home internet. So if you look at Moore's law, in the amount of time that it took Moore's law to 100x, Nielsen's law has only 57x, meaning that computational power has increased exponentially more than bandwidth. And there's several interesting things that you should also know about this. The first is that I think Nielsen's law measures something that is not truly representative of all in the whole internet. It's talking about top end, like top of the line, high end home internet connections. And the internet is not only something that connects homes to servers. There's other pieces of the internet, and there's other bottlenecks in the internet. So there's like undersea cables that can transmit terabits per second. These very high amounts of bandwidth that can interconnect each continent. There are like the data centers themselves. They have some set amount of incoming bandwidth, like AWS, all these clouds. They have a certain amount of bandwidth coming into them, and their data centers internally are interconnected by a certain amount of bandwidth. And so the internet has a capacity to transmit data. And I don't have the exact numbers in front of me, but I remember looking this up in the past. And it seems to me that Nielsen's law actually it scales a lot greater than the internet does in general. The internet's capacity is not increasing as much anywhere, nearly as much as home internet connections. And I think one reason why that is the case is because Nielsen's law is kind of like a reversion to the mean phenomenon, meaning that there's all of these internet connections out there for enterprise use cases like data centers and internet like exchange points and like corporate communications, all these things that are super fast. And home internet is like the slow end of the spectrum. And there's this thing, basically this trend that is like, it's called reversion to the mean, and things tend to revert to the mean. So like, for example, let me give you an example of something similar. So let's take growth rates of United States and China. United States started off a lot richer. China started off a lot poorer. So over the past 50 years, China has increased a lot. The wealth of China has increased a lot relative to the US. And like, it's not really a realistic expectation that the US will necessarily revert downward towards the mean, although maybe on a long enough time horizon it would. Usually economies grow at a steady rate. Similarly, like top end internet is not going to increase that, like it's not going to decrease most likely. But the things on the lower end of the spectrum are going to have an easier time coming up and getting closer. Like basically things kind of even out and average out over time. It's a general trend. So anyway, the point is that networking, communication speed does not increase as fast as compute. That's my point. And if anything, I think Nielsen's law is optimistic. I think that compute is just scales more than internet bandwidth. And I think just in case you're wondering, I believe that Nielsen's law doubles every 21 months instead of 18 months. I think that's the difference. Yeah, I'm not seeing where that is, but I'm sure it's here somewhere. Well, whatever. That's all beside the point. So compute scales more than bandwidth. That's what we're taking away from this. Okay, so now what are the implications of this? So the first thing is that any system, first of all, that's going to scale, it's going to use compute, and it's going to presumably use bandwidth, any sort of networked application. It's going to hit, at some point, it is going to hit bandwidth as a bottleneck. Bandwidth, communication, is going to be the thing that prevents it from scaling rather than compute. And so like one way that I often talk about this is I talk about this in relation to blockchains. So blockchains, they are very focused on scaling compute. And unfortunately, though, the amount of blockchain transactions that go into them is that they can't actually, they restrict the amount of data that you can put into these transactions. So although like at first the compute in these blockchain systems was very low and that was a problem, but what's happened is now these systems have actually scaled compute a lot more. And since they've done that, now compute is no longer a barrier for them, but now bandwidth is a barrier for them. And so this is why, and I won't go into this too much, but this is why like there's these new ways of actually scaling blockchain bandwidth that I think is like the key to unlocking more blockchain scaling than already currently exists. And it's basically the next frontier in the blockchain space. But one other thing that I think this shows, which is really important, is that I think over time, this trend means that a lot of things are going to become increasingly more local. So we're going to have excess capacity on our local machines, meaning our computers at home are going to be faster. They're going to have more memory. They're going to have more storage. All of these things track with Moore's law, not Nielsen's law. And so we're going to be able to do a lot more on device. And this is both in the blockchain space, which is why I brought it up. This is kind of where I came to some of these ideas, is thinking through that. So we're in the blockchain space, we're going to see a lot of networks that do a lot more work locally and do a lot less on like some node in some distributed system on the internet. And we're going to try to minimize the amount that we communicate in these protocols and maximize the amount that of resources that we use locally. And so when you apply this to AI, sorry, one second, I'm just getting a message. Okay, so when you apply this to AI, what this means is that you are going to, if this trend continues, we can expect a lot more local models. You're going to expect right now there's this huge gap where a lot of stuff cannot be run locally. But over time, Moore's law is going to scale the capacity for what we're able to do locally. And so this is a really good trend. And the other part of this is that essentially, it's going to be easier to not get to the frontier, but to get near frontier performance. Because, so like, look, let's take as an example, DeepSeek. DeepSeek was a company out of China that was able to make a model called R1 that had similar performance to that of all the leading models like O1 and Claude and all of that. And their performance was quite good. Let's just look this up really quick. DeepSeek benchmarks. Let's see. Let's pull this up. This doesn't seem like a good website for it, but wow, not good. I'm just gonna pull this up. Try this one. So here you go. Here's a good, this is good. So we're comparing DeepSeek R1 to these OpenAI O1 and O1 Mini, and you see that this is maybe not beating them, but it's getting quite close. And one of the things that really impressed people is that they were able to match this performance with a lot less compute. And I think that this trend is going to continue. And one of the reasons that this trend is going to continue is because it will is because basically, if you look at this curve, like let's go back to this, like, was it here? Where was it? Like this log curve, right? If we look at this, like, let's zoom in on this. It's actually like, let's say that you're here on the x-axis, you put in a bunch of money. Like let's say you put in 10, or maybe here's another example. If we go back to Wolfram Alpha, where was Wolfram Alpha? I guess I closed that tab. But the point is like, let's say you have a $100 million data center instead of we're talking billions now, $100 billion data center instead of a $10 billion data center. You're only getting a bit more performance for that. And so it's actually like, once you've kind of charted the path at the frontier, it's actually a lot easier of a bet for someone with like an algorithmic improvement to get the capital to come in and try to do things differently. And you basically know that at the limit, compute is not going to be a significant differentiator. And like, let's say that someone has like only 2x more capital than someone else. That one with half the capital, they're basically, it's going to be irrelevant how much less compute they have. That's not even going to register on the results. So you really need to be getting many orders of magnitude more capital in order for that to make much of a difference. Like, you just see how this is diminishing. Like, so if you have a bunch of stuff on the x-axis, you're only a little bit higher on the y-axis than you otherwise would have been. Meaning, if you have a lot more money, a lot more capital, a lot more computers, you're only going to have a little bit better results. And so this means that, like, I love Elon, but the Grok strategy of just getting the biggest data center is not, it's good because he can do it, so you might as well. But it's not going to be a long-term strategy. You need to actually, come up with better algorithms or something. It's actually hard to even, that would be a whole episode in and of itself. Like, what kind of moat can these companies bring? Because to some extent, this kind of seems like it is becoming a commodity. And I'd have to think through that and think about like what their business models should be. But generally, like I guess the good news is that it's very possible, based on these scaling laws, for an upstart to get some capital. Yes, you need capital, but to match the performance of these big companies, even though they're not going to have as much investment. And so that's a very good sign. Another really positive thing that this implies is just this argument about AI doom. Will AI kill us? So yes, we're going to build bigger and bigger systems. It's true. But we're seeing a diminishing return on this. So we're going to have to 100x, 1000x, do all of this stuff. And at some point, this is just not going to be realistic. So like, let me give you like an example. Like, I want to kind of like paint to you the situation that we've been in so far and where we currently are. And then I want to compare that to where we're going. So first, we basically had no reason to believe that this stuff would work very well. Like, we were in the early stages. It was like AI winter. We didn't know what approach was going to get us AI. We were just stumbling around. Now, the transformer architecture came out. OpenAI made some really big bets on, like, they had a great prototype with GPT-2, then they scaled it up with GPT-3, a bunch of cool stuff. They packaged it up really well in ChatGPT. All of these things are, there's a continuum of events that led to where we are now. But the point is it went from a proof of concept to an actual useful thing that was transformative technology. And that was really cool. But we were, at the time that it was a prototype, we weren't spending like giant, like $100 billion on this stuff. Okay, we were just messing around. It was like a side project for humanity. This was just things that some people worked on. It was interesting. It was promising, but we weren't like actually putting all we got into it. Now that we've seen the potential here, though, and we are now scaling up our investment immensely. So what you're going to see is results that are increasing super, super, super fast. That's going to be what you're observing in your day-to-day life. You're going to see AI just get better and better and better. And every week there's an announcement. Claude 3.7 just came out. I heard GPT-5 is coming out. Grok 3 just came out. Like, it's so good. It's so good. Everything's improving. That's because we went from side project to real project. And like, let's look at this curve. Like, here we got open O3 high. It's over $1,000 per query. So this is cool. So the thing about this, though, is like, that sounds expensive, but it's not that expensive for something really good. One other thing is that when we started this, we were just kind of messing around, like, let's generate some text and see if it's even half decent. And now we want to replace people. We want to replace employees, and we want to do these very advanced use cases. Like, you might want to pay thousands of dollars for it to code an app. Like if you go and hire some offshore people, you'd end up spending tens of thousands of dollars to build an app. Now, I would be willing to pay thousands of dollars to AI instead, maybe less than to the people, or even if it's easier to manage. I mean, I could even, if the app is better than what the people offshore would do, and if it's easier to communicate and they do a better job, you could even want to pay more. If it does a better job than engineers, like Google hires engineers and pays them $500,000 a year, and maybe they write like one feature for an important project, or I don't even know how much they do, but you get the point. They don't do that much. Perhaps AI could replace some of that. It could be worth spending hundreds of thousands or millions of dollars on advanced tasks. Right now, AI is only good for remedial tasks that can't really be trusted fully. But if you have a more competent AI, there's a huge budget for it. So this actually makes sense. It doesn't make sense to be like your chatbot. If you want to spend over $1,000 per query, that doesn't make sense as a chatbot. But to actually go up that hierarchy in cost to something that's many orders of magnitude more expensive, there's actually room at the head of the there's room at the top to continue spending more. We have a lot of different use cases that we are going to uncover. So essentially what this means is that we are rapidly applying AI to all facets of the economy, and we're willing to spend a lot more than we currently are. Like, I spend $200 per month on ChatGPT Pro. Well, I would spend more than that too on AI. Like, I could spend more than that on AI. That's what they're charging. But I could spend $1,000 a month on AI. Now, there's some amount, $10,000. I'm not going to spend $10,000 a month on AI unless I have some business case for that. Although it is possible if I did have a business case for it. But let's say that I didn't, then I wouldn't. But the point is, though, is that we will see these amazing systems with this amazing performance, and it's going to make sense. And we're going to see all of these demos and benchmarks and this crazy stuff come and happen very quickly. And that's what we've been seeing. And so the AI progress is immense. And the reason is because we're spending so little. If we just spend a lot more, it's worth it. And there's a certain amount of capacity that we still have to continue investing and continue spending on this. We're still early, and there's actually just a limit at the rate at which we can even deploy this technology. So we're still very early on. Even though our scaling is not very good, we are able to throw so many resources at this because it's this kind of like, again, reversion to the mean type of a thing, where this is not a very large amount of our spending. So we can, once we can start spending as much on this as we spend on other important things. And then once it starts to get to a very high percentage of GDP, we may not want to spend as much anymore. There's going to be a point at which our ability and or desire to put more resources towards AI, that's going to diminish itself. And so essentially, we are going to hit a plateau where we cannot put any more resources towards AI. And if we do, it's not going to make much of a difference. Now, the other reason why AI progress seems so good right now is because, like, let's look at this. I wish I could. I wish I had like a good way of like charting this stuff for you, but here, this is a good image. Look at this. Look at here. This is exponentially going up. This is logarithmically plateauing, and this is linear. This is like you put one in, you get one out. So you go 2 times the compute, you get 2 times the intelligence, right? So this is linear. At this point, there's not much difference. Like, look in the beginning. It's not much difference. These look very similar. They're all right here. they're all roughly the same. I'm not saying they're the same, but if you look just at the beginning towards 0 on the chart, these look very similar. They're all within 1 point of each other. Now, as you go outwards, as you go, you scale, you see that the exponential takes off like a rocket ship. The linear just keeps increasing, and the logarithmic just falls short. It plateaus. And you see what's called a divergence. These curves diverge. But what's kind of cool is like, let's go from I'm going to zoom in a lot here. And I'm going to try to explain this for people listening, but otherwise you're going to have to look at it. Okay, so starting at 1, 1, basically at 1 on the x-axis. Okay, the point 1. Now, in this case, this logarithmic curve is at 0. Now, when you go to 2 from 1, you go up by 1. So now this is 1, 0. Now this is 2, 1. That's for the logarithmic one. Now, for the linear one, you start at 1, 1, you go by 1, it goes from 1, 1 to 1, 2. And for the, I guess I'm kind of slightly off here, but the exponential, I mean, we could have shifted these curves. It's not perfect, but going from like 0 to 1, so if you start off let's say 0, you're at 0, 1 on this exponential, and then you go to 1, you're going to 1, 2. Or if you started at 1, you'd go to 1, 4. But the point is the difference is so minor. The difference is like, it's like at most a factor of 2. And it's an absolute value is very different. Like at the beginning, these curves don't feel like this is a pretty rapid increase. Like you doubled this, you doubled the compute here going from 1 to 2, and you doubled the result. I mean, I guess that's not really double, but you get what I'm saying. This curve, the shape of the curve, it flattens. And this gets really depressing when you go from like 6 to 7 and you barely increase the result. Whereas going from like 1 to 2, you're going from 0 to 1. It's very similar to this linear growth. And so at the beginning of the curve, it feels even better. Like even though the technical scaling properties of this at the beginning are not good, like this is like a bad trend, this is not a highly scalable system. Even though that's true, it feels pretty linear. It feels pretty good. So not only are we like willing to throw a ton of money at this to actually just scale it up because we're starting from nothing and we're scaling up like crazy. We're also at the beginning of the curve where it feels a lot better. And so why did I want to paint this in an optimistic light? Well, the reason why I wanted to paint this in an optimistic light is because, first of all, I do believe that we are going to increasingly run models locally. I think that's a trend that's going to continue to occur. I think that the capacity to run models at home is going to increase. I think that upstarts are going to be able to displace big, well-financed labs. I think that the scaling curves really show this. So we're going to see a lot of innovation. We're going to be able to see a lot of open models that work really well and we can run on device. I think all of these things are true. And I also think that people who think that AI doom is going to occur because of these models, I think they really need to contend with the fact that no matter how much these things scale, it just hits a sort of plateau. And even if you're scaling your resources many orders of magnitude greater than humanity's, like let's say an AI can harness 1 million times more energy than like all the energy that humans harness times 1 million, that's actually not that much more intelligence than humans. I mean, it's a good amount, but it's not a million times more intelligence. So the scaling simply diminishes. Now, there's one more thing that I wanted to cover. And that is this talk by, how do you even say this guy's name? Jan LeCun. LeCun? How do you say? I don't know how to say that. I'm not French. What is this one that he had? There's, oh, I should have bookmarked this before. It must be this one. So let's just skip ahead here. We're not gonna watch this whole thing. There's like this famous slide that everyone makes fun of him for, but it's not bad actually. Let me try to find this. Wait, was that it? Was this the slide? No, this is not the slide. All the slides look the same, so. Just trying to find it. Let's see if there's anyone in the chat. If you're in the chat, let me know. Say hi. Nope, nobody's chatting. All good. Okay, I don't know. I'm just gonna look this up actually. Oh, here we go. Found it. Okay. So this is the thing that he's dunked on the most for. And so he's basically, so let me just read this. So he has a slide, and by the way, he's the head of AI at Facebook, and he is a pioneer in deep learning. I think he was one of the people who really like figured out like handwriting, like how do you read handwriting with AI. But anyway, he is an AI veteran. So he has this, what he calls an unpopular opinion about autoregressive large language models. And autoregressive means that it's the kind that predicts the next token. And so like just kind of like a precursor, basically you put in a prompt that starts it out. Then it predicts what the next, like the first character or couple characters of that sequence would be. And then it takes that result and it figures out if that was the next token, what would the next token be? And it just keeps generating the text from your starting point. And so I will read what he said. So first of all, he thinks that these are doomed. I disagree with that. That I don't agree with. I think that's like a conclusion that's not supported by his theory, but his theory is correct. So he says they cannot be made factual, non-toxic, etc. There's truth to that. You are never going to be able to 100% rely on a large language model to be correct. You also are not going to be able to, I'm going to make this full screen so you guys can see this better, but you also are not going to be able to rely on humans to be correct. It's just, these are not like computers that are formally defined in a certain way and will always give the same output. These are inherently stochastic. Large language models are not fully controllable. I agree. So those are his claims, and so that's a very negative perspective on large language models. I don't agree with that, but I agree with his analysis, and he's very smart. So I wouldn't dare disagree with him on math or something like that. But okay, so let's look at what he claims. Like, what is his analysis for why this stuff is true? So he says probability E that any produced token takes us outside of the set of correct answers. And he says probability that answer of length n is correct is this. So he has this formula. And so now what I want to show you is this image on the side here. So if you look at the image here on the side, you'll see there's this big circle. And this is all possible token sequences. So that means that like you can say, "Hi, ChatGPT, explain to me what is the capital of France." It could say dog. It could say surfing. It could say, "Hi, my name is Claude, and I like apples," or whatever. It could say all kinds of things, or it could say blah 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 blah. Right? It could say any number of things. Like it could be like just completely incomprehensible. That is the entire set here of all tokens. Now, there is what he calls a tree of correct answers. So this is like the things that you want to hear. So let me give you some examples. So you say, what is the capital of Paris? Now, if it says, what is the capital of France? If it says Paris, period, that was correct. Cool, that's one of them. Or if it said, the capital of France is Paris, or certainly, I can answer that. The capital of France is Paris. Like all of these are correct answers. And clearly, there are some answers that are correct and some answers that are not correct. This is just fundamentally true. So people who don't agree with this, like you have to like look at the combinatorics of the tokens. Like it's definitely true that there are a bunch of answers that it could put out that are going to be wrong. Like it could say Rome, for example. That's wrong. That's not correct. Most answers are wrong. And there's only certain ones. We can come up with lots of them. I'm not saying it's a tiny set, but out of all possible sets, including gibberish that it could output, all of them are it's a small portion of them. And then there's this idea, though. There's this important concept of that the error builds the more that you are putting out tokens. So let me give you an example of why this is true. So let's say that it just says Paris. What is the capital? Paris. Okay, well, that's 100% right. It's already right. That's just a fact. It's correct. Paris. It's done. That was a correct answer. And so it could say the capital of, and then stop. Or the capital of France is, now you want it to say Paris. Okay. That's true. You want it to say Paris next, and so far it's on the right track. It could be right, but if it says Rome, it's not going to be right. But what if it said the capital of Italy is? Now, the issue with that is that, okay, it could be, this is like already philosophically tricky, but let's not analyze the philosophy of like what it should say there. It already went down the wrong path. And so it could say that the capital of Italy is Paris. That's wrong. The capital of Italy is Rome. That's right and wrong in a sense, right? All these things are wrong. And yes, it could technically recover, but I think like it could say the capital of Italy is Rome. Just kidding. Actually, you were talking about France and it's Paris. Like you could say that. You could do all of that. These are within the set, but you see how you can kind of get on the wrong track, and it can think about how now they use chains of thought. So let's imagine that this chain of thought was really bad, and the chain of thought was saying like France is in Africa, and so let's look at all the capital cities of Africa. Okay, there's like Nairobi, and okay, it must be Nairobi, right? It's like that was getting it on the wrong track, and now it's completing that since the past tokens are feeding into the next tokens, it is true that having tokens added to the sequence that are basically reducing the possibility, the error in the ones that were already produced will then feed into the next ones. I think that this is absolutely true. And I've tried to do research to disprove this, and I've so far not found anyone who's actually had a theoretical argument against this. I think this is completely correct, and it just makes sense. It makes sense that basically as you continue producing tokens, exponentially the error will increase. So if you just continue running a large language model indefinitely, it will start to go off the rails after a certain amount of time. Now, everyone hates on him for this. Why do they hate on him? They hate on him for this because they think that large language models scale really well and are really good. And they're correct. They do. They do scale really well and they are really good. And so, but I think the answer is not that he's wrong. The answer is just that the error is very small and there are mechanisms that kind of bring it back to earth. So it gets off the wrong track and that's just one message. And then you message it back and you say, hey, like that was not what I meant. Like I actually, or you just ask a follow-up question, and all these things kind of steer it back in the right direction. Even if it says something wrong and you're like, I didn't think that was true. Or you're just like, oh, it didn't work or whatever. That brings it closer to reality again. And so when you have like the way that we use these large language models, and we're not generating a very long string of text, we're generating a medium, honestly, in the grand scheme of things, a short string of text. And there's a lot of iterations that pull it back into reality. So the way that it's used, we can get very good results. This is not bearish on LLMs. And that's why I disagree with his conclusion, but his theory is correct. And so now, that's why I wanted to, but first of all, before I do that, I just wanted to say I'm going to add this video to my sources playlist on my channel. So if you like this kind of stuff, like be sure to subscribe. I talk a lot about AI and I just cover tech and all kinds of things like this. So subscribe, like this video. But regardless, my point, that the reason why I brought this up is I want to relate this to this discussion of AI doom. And AI doom, like one thing that people often make a mistake of is that they think that the AI is going to basically be able to make a very long-term plan, and it's going to be super smart, and it's going to be at a super high scale, and it's going to just be able to execute on this super long-term plan that basically maximizes the number of paper clips and ends up killing everybody, something along those lines. And if you actually look at the scaling laws of AI and you look at the empirical performance of these models, what you see is twofold. One, as I had previously discussed, you see that if you add a bunch more resources, it doesn't actually get much smarter. Like it gets really smart. I'm not saying it's a useless technology. It's a fantastic technology, but it doesn't get that much smarter for the amount that you're putting in. There's a diminishing return. And basically the more that an AI is running and pursuing a goal and is basically trying to predict things further out into the future without actually getting empirical data. Like let's say an AI is making a plan. If it's strategically making a plan, it's not actually executing that plan and getting pulled back to reality. So it's going to be just like humans who have a hard time predicting the future. AI, we have a mathematical model here that shows that AI has a hard time emitting a long string of tokens that and basically thinking about very complex long-running problems. It will exponentially diverge from reality, and the error will grow. So this is something that basically is a reason for optimism because it works in reality. It's very useful. We find it very useful, and it's going to continue to get better. We're just at the beginning of this scaling, but it's not something that is going to just be able to predict the future very far out. It's not going to be able to really scale like that much at the limit, and there's a lot of reasons why basically there's a diminishing returns and the error compounds. So that was basically what I wanted to cover today. And I will be back tomorrow with another one. So thank you so much for tuning in. I will talk to you all tomorrow.